Spinodal decomposition. Spinodal decomposition is a mechanism by which a single thermodynamic phase spontaneously, i.e., without nucleation, separates into two phases. Decomposition occurs when there is no thermodynamic barrier to phase separation. As a result, phase separation via decomposition does not require the nucleation events resulting from thermodynamic fluctuations, which normally trigger phase separation. Spinodal decomposition is observed, for example, when mixtures of metals or polymers separate into two coexisting phases, each rich in one species and poor in the other. When the two phases emerge in approximately equal proportion, each occupying about the same volume or area, they form characteristic intertwined structures that gradually coarsen. See animation. The dynamics of spinodal decomposition are commonly modeled using the Cahn-Hilliard equation. Spinodal decomposition is fundamentally different from nucleation and growth. When there is a nucleation barrier to the formation of a second phase, the system takes time to overcome that barrier. As there is no barrier by definition to spinodal decomposition, some fluctuations in the order parameter that characterizes the phase start growing instantly. Furthermore, in spinodal decomposition, the two distinct phases start growing in any location uniformly throughout the volume, whereas a nucleated phase change begins at a discrete number of points. Spinodal decomposition occurs when a homogeneous phase becomes thermodynamically unstable. An unstable phase lies at a maximum in free energy. In contrast, nucleation and growth occurs when a homogeneous phase becomes metastable. That is, another biphasic system becomes lower in free energy, but the homogeneous phase remains at a local minimum in free energy, and so is resistant to small fluctuations. J. Willard Gibbs described two criteria for a metastable phase: that it must remain stable against a small change over a large area, and that it must remain stable against a large change over a small area. History. In the early 1940s, Bradley reported the observation of sidebands around the Bragg peaks of the X-ray diffraction pattern from a Cahn alloy that had been quenched and then annealed inside the miscibility gap. Further observations on the same alloy were made by Daniel and Lipson, who demonstrated that the sidebands could be explained by a periodic modulation of composition in the directions. From the spacing of the sidebands, they were able to determine the wavelength of the modulation, which was of the order of 100 angstroms. The growth of a composition modulation in an initially homogeneous alloy implies uphill diffusion or a negative diffusion coefficient. Hecker and Dalinger had already predicted a negative diffusivity inside the spinodal region of a binary system, but their treatments could not account for the growth of a modulation of a particular wavelength. In fact, any model based on Fick's law yields a physically unacceptable solution when the diffusion coefficient is negative. The first explanation of the periodicity was given by Max Hilliard in his 1955 doctoral dissertation at MIT. Starting with a regular solution model, he derived a flux equation for one-dimensional diffusion on a discrete lattice. This equation differed from the usual one by the inclusion of a term which allowed for the effect on the driving force of the interfacial energy between adjacent interatomic planes that differed in composition. Hilliard solved the flux equation numerically and found that inside the spinodal it yielded a periodic variation of composition with distance. Furthermore, the wavelength of the modulation was of the same order as that observed in the Cahn alloys. Building on Hilliard's work, a more flexible continuum model was subsequently developed by John W. The strains are significant that they dictate the ultimate morphology of the decomposition in anisotropic materials. Cahn-Hilliard model for spinodal decomposition. Dynamics of spinodal decomposition when molecules move via diffusion. Phase diagram. This type of phase transformation is known as spinodal decomposition and can be illustrated on a phase diagram exhibiting a miscibility gap. Thus, phase separation occurs whenever a material transitions into the unstable region of the phase diagram. The boundary of the unstable region inside the binodal is a region called the spinodal, which is found by determining where the curvature of the free energy curve is negative. The binodal and spinodal meet at the critical point. It is when a material is moved into the spinodal region of the phase diagram that spinodal decomposition can occur. The free energy curve is plotted as a function of composition for a temperature below the convolute temperature. T equilibrium phase compositions are those corresponding to the free energy minima. Regions of negative curvature 2/C20 lie within the inflection points of the curve 2/C2 equals 0, which are called the spinodes. Their locus as a function of temperature defines the spinodal curve. For compositions within the spinodal, a homogeneous solution is unstable against infinitesimal fluctuations in density or composition, and there is no thermodynamic barrier to the growth of a new phase. Thus, the spinodal represents the limit of physical and chemical stability. To reach the spinodal region of the phase diagram, a transition must take the material through the binodal region or the critical point. Often phase separation will occur via nucleation during this transition, and spinodal decomposition will not be observed. To observe spinodal decomposition, a very fast transition, often called a quench, is required to move from the stable to the spinodal unstable region of the phase diagram. In some systems, ordering of the material leads to a compositional instability, and this is known as a conditional spinodal, e.g. in the feldspars. Coherency strains, Fourier transform, dynamics in K-space, spinodal architected materials. Spinodal phase decomposition has been used to generate architected materials by interpreting one phase as solid and the other phase as void. These spinodal architected materials present interesting mechanical properties such as high energy absorption, insensitivity to imperfections, and high strength-to-weight ratio. Furthermore, by controlling the phase separation, i.e. controlling the proportion of materials, and or imposing preferential directions in the decompositions, one can control the density and preferential directions, effectively tuning the strength, weight, and anisotropy of the resulting architected material. Another interesting property of spinodal materials is the capability of seamlessly transition between different classes, orientations, and densities, enabling manufacturing of effectively multi-material structures.